Welcome to the Deep Dive. We're the show that takes source material you send us and, well, we try to pull out the most important insights, giving you a bit of a shortcut to getting really informed on complex topics. Today, we're looking into something pretty fascinating in AI chip design. You sent over this deep dive on something called the Tensor Manipulation Unit, or TMU, and it brings up some really interesting questions about making AI faster, but also, more efficient.
That's right. For quite a while now, the main focus in designing these AI chips, these systems on chip or SoCs, has really been about boosting the raw number crunching power for the AI models. We've seen huge steps forward there. But this source, it points to something often missed, a real bottleneck, just moving the data around. So our goal today is to kind of unpack why moving data is such a big deal, what's wrong with how we do it now, and how this new tensor manipulation unit idea tries to tackle those problems.
Okay, let's dig into that. We all know artificial neural networks, ANNs, they're kind of everywhere now, right? Data centers, your phone. And we've seen amazing specialized chips like TPUs, tensor processing units, which are brilliant at, well, the heavy math for AI inference. But this research argues something else is slowing us down. What's the actual challenge here?
Well, what's really interesting is how the paper highlights this split. Computation, super accelerated. But this other critical job, tensor manipulation, it's been kind of left behind, not really optimized. You can think of tensors as these big, multidimensional blocks of data that the ANNs chew on, and these manipulation steps, they involve shifting huge amounts of this data, but with very little actual math involved. They're like the stage hands moving props between the big computational scenes.
So it's not the complex calculations slowing things down anymore. It's more like the logistics, getting the data to the right place at the right time.
That's a good way to put it. The source shows how these data movement intensive operators, they call them tensor manipulation or TM operators, have sort of quietly become a major performance drag. If you look at their benchmarks, figure 1 in the sources, it's pretty telling. Operations like bboxcal for object detection or pixel shuffle and super resolution, they actually take much longer than many compute operations, even on a really powerful GPU, like an NVIDIA RTX 3080. In one example they give, the EDSR model, these TM operators add up to over 40% of the total time it takes to run an inference. That's significant.
That seems really counterintuitive, though. Why would just shuffling data around be so slow?
Yeah, that's the key question, isn't it? Why the long latency? And the root cause seems to be how much these TM operators need to talk to off-chip memory. Think about how memory works in layers, fast cache close by, slower main memory further away. Traditional AI accelerators, when they need to do these manipulations, often end up having to pull data all the way from that slower off-chip DRAM, move it across the chip, maybe rearrange it, and then push it back, sometimes multiple times. It's just really inefficient.
All that back and forth.
Yeah.
Okay, so what does that imply for the solutions people are using now? Are there other chips trying to fix this?
There have been attempts, definitely. Academics have experimented with things like FPGAs or other kinds of specialized accelerators. And commercial AI chips, like the NVIDIA Jetson or Huawei's Ascend chips, they often include things like vision engines or memory transfer engines. But, and this is a big but, a key limitation in almost all those previous designs is that they rely on fixed function logic, meaning they're hardwired to do only a specific predefined set of data movements.
So they're not flexible.
Not really. If a new AI model comes along with a slightly different way of rearranging data or a completely new type of manipulation,
hmm
these fixed systems either can't do it, or they need a really expensive hardware redesign, or they fall back to doing it slowly in software, which kind of defeats the whole point. They just can't keep up with how fast AI models evolve.
Okay, so that rigidity is the problem.
Mm.
Which brings us then to the core idea here.
Yeah.
The Tensor Manipulation Unit, the TMU.
Yeah.
How does this proposed design get around those limitations?
So the TMU is built from the ground up specifically for these data movement tasks. Its design is based on two main ideas. It's reconfigurable, and it's a near memory block. Near memory means it sits physically very close to the memory controllers, right near where the data lives.
Cutting down that travel distance we talked about.
Exactly, minimizing those costly trips back and forth to off-chip memory.
And reconfigurable, that sounds like the direct answer to the fixed function issue.
It is. That's really the key innovation for flexibility. Unlike those fixed approaches, the TMU uses what they call a RISC-inspired execution model. Think simple, efficient instructions like a general-purpose CPU.
Yep.
And it has this unified addressing abstraction, which is basically a smart, consistent way for it to view and access memory patterns. This combination allows it to be programmed, essentially. It has reconfigurable registers, so it can adapt to all sorts of different TM operators, both current and future ones, without needing new hardware. It kind of encodes these complex data shuffling patterns using parameterized matrices, which makes it very adaptable.
Okay, that makes sense. So given this flexibility, what kinds of manipulations can it actually handle? The source mentioned coarse-grained and fine-grained. Could you give us some examples?
Sure. Let's start with fine-grained. These operate often at the byte level, manipulating individual data elements, like rearrange. This could be transforming data from a standard camera format, say RGB, into a different channel layout that's better for the next computation step, optimizing memory access. Or resize. You see this everywhere in computer vision scaling images up or down using methods like bilinear interpolation. It's fundamental, but involves lots of small adjustments. Then there's bbox scal. This one's interesting. It's used in object detection to pull out the coordinates of the detected bounding boxes. Not much math, but lots of data filtering and formatting. Very latency sensitive in real-time systems. And MG2 call, which is a classic one, it reshapes image patches into columns to make them ready for standard convolution operations. Pure data reorganization. Then you have the coarse-grained operators. These deal with larger chunks of tensors, more about changing the overall structure or dimensions. Things like transpose, just flipping the dimensions of a tensor, or ROT90 for rotating images, pretty common. Pixel shuffle and its counterpart, pixel unshuffle. You see these a lot in super resolution, where they rearrange pixel data between the channel and spatial dimensions to change the image size. Upsample is another scaling one, making feature maps larger. And then operations like root, split, or add, which manage how data flows through different paths in a network, combining tensor blocks, dividing them, or adding them together element by element.
Wow, okay. That covers a really wide range of necessary but often overlooked operations. So how does this TMU actually fit into the bigger picture, into an AI chip that likely already has a powerful TPU? Do they work together?
Yeah, they're designed to be complementary. The TMU isn't trying to replace the TTU, which is the computational powerhouse. Think of the TMU as a highly efficient assistant processor that sits right next to the direct memory access engine, the DMA.
The DMA being the chip's main data mover.
Right. So the TMU, being right there, can grab tensor data directly from memory via the DMA, manipulate it, resize it, rearrange it, whatever's needed, and then either feed it straight to the TPU in the perfect format or send the process results back out to DRAM. And it uses some clever tricks to keep things flowing smoothly, like tensor prefetching. It uses double buffering, so it's already loading the next chunk of data while it's working on the current one.
Keeping the pipeline full.
And output forwarding, which lets the TMU start processing data bits even before the TPU is totally finished with its previous calculation. It minimizes idle time for both units.
Okay, this is where it gets really interesting. What kind of performance boost does this actually deliver? What are the numbers?
The results they report are pretty striking. When they benchmarked individual TM operators, the TMU showed huge speedups. For example, the resize operation was up to, wait for it, 1,413 times faster than doing it on an ARM A72 CPU.
1,400 times.
Yeah. And 8.5 times faster than the specialized engine on an NVIDIA Jetson TX2. For bbox scal, it was over 55 times faster than the CPU. And they normalized these numbers for memory bandwidth differences, so it's highlighting the TMU's core efficiency.
That's a massive improvement for those specific tasks. But what about the overall impact? Running a whole neural network end-to-end.
That's the crucial test, right? And when they integrated the TMU with their own TPU design, the complete system showed significant drops in overall inference time. For instance, they saw a 34.6% reduction in latency for models like YOLUF-8, that's a popular object detection model, and also for attention models, which are key for things like large language models. And if you look just at the time spent on the TM operations within those networks, the TMU managed to cut that accumulated latency down by over 90% in several key models, like 93.9% for YOLUF-8. It basically almost eliminates that specific bottleneck.
So huge speedups.
Yeah.
But what about the cost? Adding new hardware always means more silicon, more power. Is it efficient in that sense?
That's another really strong point in its favor. The actual fabricated TMU chip, using a reasonably modern 40mm process, is tiny, only 0.019 square millimeters. To give you an idea, they compared it to another academic data movement accelerator, the AME, and the TMU was over 15 times smaller. And importantly, when they integrated it alongside their TPU, the TMU added only about 0.07% extra silicon area. It's negligible overhead.
Wow, 0.07%. That's tiny for that kind of performance gain.
It really is. And the power consumption is also very low, around 2.7 milliwatts. So small footprint, low power. It makes it very practical to include in modern AI chips, even for devices where power and size are critical.
So wrapping this up, this deep dive into the Tensor Manipulation Unit, it really feels like it signals a significant shift, maybe, in how we should think about designing AI chips. It's not just about raw FOPS or TOPS anymore. It's equally about this intricate dance of data.
I think that's right. By really targeting these data movement heavy operations with a design that's both reconfigurable and sits close to memory, the TMU offers a way to seriously boost overall system speed for modern AI tasks. It lets these networks run much faster, more efficiently, and critically with very little extra hardware cost.
It really underscores that sometimes the fastest path isn't just more computation, but maybe just clearing the way, making sure the data can get where it needs to go when it needs to get there. It leaves you wondering, how might this intense focus on optimizing data movement, not just the computation itself, fundamentally reshape how we design AI hardware in the future? And could it even influence how AI models themselves are built, perhaps leading to architectures that are inherently more data movement friendly?